Hi, I'm Professor Angela Rasmussen from the Department of Electrical and Computer Engineering at the University of Utah. Today I wanted to go over some diodes called the Zener Diode and then also talk about the power supply. So the Zener Diode, so this is going to just be a lot of background information. And so the Zener Diode's graph looks like this, where in the forward direction, it has the same curve that we have seen for a normal diode, but in the backwards direction, it actually gives you this nice curve here where once you reach this minus VZ0, then it will turn it on and let current flow in the opposite direction. So this is very useful for a voltage regulator. As you can see that the voltage doesn't stay exactly at that VZ0, that's kind of your ideal voltage. So that might be a 5 volts, meaning that you would have a plus or minus 5 volts across it. But in reality, it doesn't quite stay there, and so you're going to go up and down a little bit around that 5 volts. What you want to do is try to minimize that range by keeping it in a very small range. So this is the Zener diode model. It has both a voltage and a resistance, which is slightly different than what we've used for the constant diode model. And so we can use this when we analyze a circuit that has the Zener in it. So a regulator provides an approximate constant output voltage, V0. Like I said, it could be, for example, 5 volts. Zeners are rated at a specific voltage. It can be 5 volts, 3.3 volts, 10 volts. I'll show you different values in a minute. And it keeps it approximately constant around that value. So it is a useful device to be able to create that. And these are some other measurements: line regulation and load regulation, which is just the changes in output over the changes in input for the line and the change in output over the change in current for the load. We're not going to get into details on those, but just wanted to introduce those terminology to you. So most of the time, this is how you're going to hook up a Zener diode. You're going to have some circuit, and this will be a Thevenin equivalent of whatever that circuit is. So it's broken down into a voltage and one resistor. And then you're going to place your Zener here, and it's going to look like this. So your Zener will have the bar side of it going up, and that is going to keep the plus minus whatever rated voltage that you want. The RL is going to be your load, and this is going to be, for any simulation that you do, it is going to be a model of your load. So, for example, if you know that you have current that is drawn at 100 milliamps, and you know you need to keep it, let me write this a little different. So you want to keep it at, say, 5 volts. So you know you want a specific output. So if at this node you want to keep 5 volts out, and you know you also need to be able to pull through this 100 milliamps, you can model that by an RL of your voltage over current using Ohm's law. So that's going to be 5 over 100 milli. So that will give you your value of what you want to use for your RL value. So the design for the Zener diode, the issue is that we need to make sure that we have enough current flow through here to turn on the diode. So there is a minimum current that needs to go through it, IZT, of 25 milliamps. That means that there needs to be enough draw through here that will split and pull some through here and some through here. When students usually hook this up, they don't get enough current, and so they aren't able to turn on the Zener diode to actually work correctly. So here I've already gone through the detailed numbers. So from a data sheet, you can read off VZ, which is going to be your rating for it. That's the VZ0. So for example, at 10 volts is achieved when we have that current going through it of 25 milliamps. The RZ is given on that data sheet of 7 ohms. And we have an IZT then is going to be the 25 milliamps, and then the knee IZK is 0.25 milliamps. So we can analyze this, take voltage loops and go down, and what we see is for this example, R1 needs to be 26 ohms. Notice also going through that if your voltage is at 17 and you go down to almost 9 volts, or 9.8 volts, the power in that resistor is going to be 2 watts. So when you build this, you need to make sure that your ratings for your resistors that you use is much better than a 1 watt, if you need 2 watts. So the ratings in the resistors that you've seen so far have only been a 4th watt rated resistors. So make sure you get the higher rated resistors, and that that it will match what power rating you're expecting from this if you build these. So so the Zener, this is a sorry, I thought I'd added this in the other way. So reading this is going to be difficult. So the other side of this, there we go. So here is that sheet with the ratings on it, blown up a little bit more. So if we want to have, say, that 10 volt, we'll look in this column. We'll go down to the voltage that we want. For example, this would be the 10 volt. This would be the Zener diode number that we would want, 1N4740. You can see here, this is there is your IZT, milliamps, and your 7 ohms. And then it gives you the other information that will be, give you more details. But basically, you need to get 25 milliamps through that Zener diode in order to get that around 10 volts supply. If you want a different Zener, say you only want 5 volts, the 5.1 looks like it's going to be about the closest one to 5 volts. And so you would choose this Zener number. So for a power supply, I'm skipping ahead. So this is an overall layout of the power supply. So you need to have a voltage regulator, and that can be a Zener diode or a regulator chip. And then you also need a capacitor to act as a filter to filter out some of the signal, and you need a diode rectifier. So these are the different parts of the circuit. We're going to start with a line voltage. So this would be where you would plug it into the wall. So this is your wall. You're going to plug it into the wall. You're going to use what's called this power transformer. And these are in the lab that you can check out, so you don't have to buy the power transformers. The rectifier, then, what you want to do is take it, because you can see it has a positive side and a negative side of your sinusoid. The power transformer transforms it down from 120 volts. It's going to bring it down to something more reasonable like 40 volts. And then from there, you want to change it so it's unilateral, meaning only one side. So you want it to be all positive for the positive supply and all negative for the negative supply. Then you want to filter out so that as you add a filter, you're going to have some ripple going into the regulator, but then that ripple is going to be reduced even more by that Zener diode or regulator chip. So this is how a power supply actually works. So going back, if you want to use the chip, this is those components. This is the power transformer, and in your simulation, you're going to simulate all of this portion with just a sinusoidal source. So if you measure in lab from the power transformer, you know, a 40 volt peak to peak, then that's what you're going to substitute in here as a 40 volt peak to peak power supply, and not worry about simulating the transformer side of it. Then you're going to have a wave rectifier. You can have a full wave or a half wave. There's different rectifiers. We'll go over those next. You're going to have your capacitor, and then you're going to have your Zener here, or you're going to put in the chip. This shows the chip. If you use a chip, then you want to make sure that you have at least a couple volts above the rating. So on here, this shows you the LM78XX. Sorry, this is sideways, but the stockroom has these chips if you want to use them. And then again, just put 2 volts above what you want out, because it will drop it down by 2 volts. So if you expect out 10 volts, it will actually give you 8 volts out. So you want to be careful that you choose the right number. So for these, the 7805 gives you 5 volts out, and the positive one is with the 8, and the negative one is with the 9. And so you want either LM78, so there's a 5, a 12, a 15. So you kind of want to make sure which one you want for your voltage ranges. So for 12 volts would be the 12 on the ends. For 15 volts would be this, so you would need to make sure you're supplying 17 volts before this chip to get the 15 volts out. And for the 12 volts, you need to make sure you're supplying 14 volts, otherwise it won't turn on the chip. We don't have a model in PSpice for the linear regulator chips, so I suggest that you do the simulation at least just with the Zener diodes. So the other component that I was showing you is that half-wave rectifier, or wave rectifier. So what a rectifier does is it takes your sinusoid that is positive and negative, and now it's going to rectify it so that it only turns on the diode when it's positive, and then it turns off the diode when it's negative. You can switch the diode around in the other direction. So if you swap this going the other way, it's going to pass it through as a negative and all be negative values. So when you want to make the negative supply, you're going to flip this around to give you the negative. When you add on the capacitor, you can see here what happens to the capacitor side is that you get a decay once that capacitor is charged up, and this is where your ripple happens. If you add in now your Zener between here and here, you're going to make that even flatter at this node. Full wave rectification can also be done, and you can see that the ripple is less. So this is the circuit for a full wave rectifier where you have 2 diodes. And then when you do both sides, this is called a bridge rectifier. There is a bridge rectifier chip that you can use. And the difference between a full wave rectifier is that you have a 0.7 volt drop from your original, so you need to make sure you're counting for all these drops so that you have enough voltage to supply either the Zener or the linear regulator chip. And you get 1.4 volt drop from the original for the bridge rectifier. So the peak rectifier, which is that capacitor in there. So this is modeled just how you're going to have it, where you have, this will be an actual sinusoid, and then you're going to have your half wave or full wave rectifier at the diode, and then this is your filter, this peak rectifier, and then you're going to add in between here and here will be your Zener or your chip, and then RL is going to be your load. So the equations for the capacitor that you're going to be wanting to understand is for the current. So your current is going to be dependent on, so your maximum current is going to be dependent on these. So the voltage at the peak, this is before your diode, so this is coming out of your power transformer. RL, I already described earlier, that's your load. And then your omega in this is going to be 2 pi of your frequency, and your frequency from the wall is going to be 60 hertz. And VR is your ripple. And then your capacitor that I'll show you how to get a value for right now. And then that RL again, and then again VP. And so all of these values, you know what they are, and so you can calculate what the maximum is. So the capacitor, though, is easy enough to get an approximate value at the beginning. If you use a full wave rectifier, you can use this. It's just a half of your current IL, which is, in the case example I gave before, that was like 100 milliamps. And the frequency is 60 hertz. And so if you want to design it so you plug in what value of ripple you want, if you want to try to aim for a 0.01 volt ripple, you would put that in here. If you want a different value, if you want a 1 volt ripple, you can do that, and then solve this equation to get a capacitor value as a starting value. You want to then understand that the relationship between the ripple and the capacitor is inverse, so if your capacitor goes up, your ripple goes down. There is a disadvantage about having too high of a capacitor, because then it takes a really long time to charge. And so there's going to be a happy medium, and you're going to use the simulator to find what that happy medium is, but that is a way to get a starting value for your capacitor. So here's an example I just wanted to show you of an actual, this was an ATX power supply, and you can see it looks very complicated, and it is. In here, I wanted to just show you that you can see there's a couple components that I've already talked about. So here you see a bridge rectifier, and then you see the capacitor, and then the Zener diode, and then the rest of this is kind of a load onto there. So after that, there goes a load. So there's one power supply. And then over here, it uses a negative voltage regulator chip to give you the negative 5 out. And you have on there, you have this capacitor, and then your resistors. So this is just an example just to show you how complicated it can get. But you can start off with a very simple design, and I've already shown you an example schematic that you can start with. I went through how you can design the capacitors. So these values are going to be, this is going to be your positive, this one is going to be your negative side. So here if you wanted minus 10 volts out, and here if you wanted plus 10 volts out, then you're going to orient those capacitors in that direction. So the diode's oriented here. This is a full wave rectifier. Again, you can substitute this for a bridge rectifier or a half wave rectifier, your choice on here. This is modeling the input from the wall plus the power transformer. So this is after that. So you need to choose the right amplitude based on what you measure from the power transformer that you use. That value may be 50 volts, it may be 20 volts. You're going to get different values there. So measure what you're going to use. It varies quite drastically between each one, so make sure you know which power transformer you're using. And then here you're going to design that R1 and R3, similar to how I went through the example above. And then you want to choose the right Zener based on if you want 10 volts, 15 volts, 12 volts, sorry, that was negative, etc. You get to choose as the designer what value you actually want, and that's going to be determined by which Zener you're choosing. So this is your RL, and that's going to be based on what current you measure from your circuit, knowing you need how much value. So if you need 100 milliamps, then you would, and you're using 10 volts, you'll take 10 over 100 milliamps as the value for this RL. And then in the project folder, you can see the rubrics of what else you need to print out and calculate. Remember, I went through this IL, just is the load current. This is IL. And then you're going to get, again, you're going to get a maximum value and then a minimum value. So if you design it to be around 10 volts, you might get 10.01. And then for V out min, you might get 9.99. So you have to zoom in on the graph to be able to see what that small ripple is. That's also what you're going to plot here. And then plot all of the currents. So you want to make sure you know what currents are going through each of the components. And then you also want to see the power in them so that when you build this, you also know that the power is not going to be blowing these up, and you get the right wattage ratings for each of these components. That concludes this description of the Zener diode and the power supply. Thanks for watching.